Okay, so welcome to lesson 6 of our revision course. This lesson is titled Conservation of Mechanical Energy, and our learning objectives for this lesson is that, as always, by the end of this lesson, at least you should be able to state the principle of conservation. So here it is something, it's conservation, the principle of conservation of mechanical energy, the principle of conservation of mechanical energy, and also you should be able to perform calculations using the formula for this principle. So without wasting any time, let us just get straight into it. So, in simple terms, the principle of conservation of mechanical energy states that, and you should be able to state this definition in an exam. It says that the total mechanical energy in an isolated system, keyword there being isolated. Remember, we've spoken about what an isolated system is when we're dealing with the conservation of momentum, and we're talking about elastic and inelastic collisions. So it says that the total mechanical energy in an isolated system remains constant or is conserved. The law of conservation of mechanical energy applies when there is no friction. So remember, in an isolated system, we don't consider the effect of external forces. So we said that friction, for example, is an external force or even air resistance in this case. So there is no friction or air resistance acting on the object. So, in the absence of air friction or any other external forces, the mechanical energy of an object in the Earth's gravitational field is in what we call a free fall and is conserved. So, in general, this principle comes from the general law of or general principle of conservation of energy, which says that energy cannot be created, destroyed, only transferred or transformed from one form to the next. But then before we actually get deeper into this, we first have to understand, what do we mean when we talk about mechanical energy? So what do we mean when we talk about mechanical energy? So mechanical energy in physics term. Let's say we'll say that E represents mechanical energy. It is the sum, so we're adding two things. It is the sum of the kinetic energy. We've already spoken about kinetic energy, and now we're going to be introducing you to another thing, which is potential energy, and we represent that by the letter P. So don't confuse this with momentum, it's just potential energy. And like we've mentioned, that we've already defined that kinetic energy is given by a half mv squared, where this is the mass of the object in question, this is the velocity. So remember, the mass is in kilograms, that's the SI unit, and this will be in meters per second. And then now potential energy is actually given by mgh. So this is the mass of the object in question, and this is the gravitation. This is the gravitational acceleration. You already know this value. Remember, that value is equals to 9.8 meters per second squared. So these are some of the information that you actually are familiar with. And now this is the height. So when we talk about potential energy, you realize that we often talk about the height. The height will be measured in meters. So let us just move on right along. So now mechanical energy is actually in fact just the sum of this. So we say mechanical energy EMAC equals to a half mv squared plus mgh. So that is it. But now when we talk about the principle of conservation of mechanical energy, so it says that the mechanical energy, perhaps at an initial point. So let's say we had a sort of a roller coaster ride, and we had an object. Let's call this object A, another object, we call it object B. And this is the initial position of that, and this is the final position. So that principle, what is basically saying is that the mechanical energy here, as well at the initial position is going to be equals to the mechanical energy here. So this means that Emec at initial position represented by I will be equals to Emec at the final position represented by F. So meaning we'll have kinetic energy here, which is given by a half mv squared initial plus mg, and then this maybe would be your initial height hi, then this will be hf, so hi. And then also on this side we'll have a half mv, so the final velocity of that object at point B, I'm lying, squared, plus mghf, so this is the final height. So that is basically what this principle means in terms of mathematics, and you should be able to understand this. So the total mechanical energy here at the start, or at the initial position, is equals to the total mechanical energy at the final position. Okay, so we have a question here, and it says that a 2 kg ball rolls on a toy roller coaster from A at 200 meters above ground to B, where the height is 16 meters, and it has a velocity of 14 meters per second, and then calculate the ball's initial velocity. So let us attempt to draw the situation. So we have a toy roller coaster, and we moving from this point here, we call this point A, and then we call this point B, and the initial height here is 20 meters. The final height of the ball is 16 meters, and then the initial velocity here we're not given, that's what we're trying to find. And what else, but we given the final velocity of the ball here, which is 14 meters. I don't know why I always write that way, which is, say, VF is 14 meters per second. Okay, so now we have everything that we need. We've described the situation, and we're going to use that formula, that principle of mechanical energy, or the conservation of mechanical energy, to answer this question. Okay, so remember now we said that mechanical energy at the initial position will be equal to mechanical energy at the final position. This is our initial position, this is our final position of that ball. So we have a half mvi squared plus mghi. So this is the height, initial velocity of that ball, and then after that it should be equal to mvf squared, so this is kinetic energy, plus mghf, so this is the final height. And now it's just a matter of substituting everything. So we have a half 2, and then we don't know what that velocity is, that's what we're calculating. And then we have the mass 2, we know that is 9.8 g, is 9.8, it's at a height of 20 meters, which is equals to a half 2 kg. The final velocity of that is 14, plus, remember to square that, the mass is 2, g is 9.8, and then we have the height, the final height of that ball is 16 meters. So now it's just a matter of putting everything in a calculator and just making sure you get the right values. So if you put this in a calculator, this is what you're gonna find. If you put the on the right hand side, if you put everything in a calculator, you're gonna come to a value of 509.6, and on this side you'll have vi squared plus 392. So just make sure that you actually get the same answer, and then it's just a matter of taking this to the other side, then it becomes negative. So vi squared is given by 509.6 minus 392. So vi squared is actually just 117.6 Apologies for that. And then to remove the square root, you just introduce the square root on both sides, and you find vi to be plus or minus 10.84 meters per second. But we know that this thing is actually moving to the right, so we can define that position as positive to the right, and this one is negative. So meaning our answer in a chalk field will just be vi is equals to 10.84 to the right. Okay, cool. So this actually brings us to the end of this lesson. This is an important concept to know and understand, especially when later lessons, when we're going to be talking about work and work, energy and power. So make sure that you remember all of this for those later lessons. Thank you so much for watching.